organizers for setting up this nice conference. So my name is Gonzalo Manzano. I work in the Institute for Cross-Disciplinary Physics and Complex Systems in Mallorca, where I recently became permanent. And I'm going to present a work in collaboration with some people at ICTP, with Ludmila Paiotti and Rosario Fazio, and Marcus Huber from the UT Vienna. So we're going to talk about the possibility of using a time crystal in order to count time, because in order to build a quantum clock. And we will focus on analyzing the performance of this clock. So let me start just by a brief motivation. So time is one of the most fundamental concepts in physics and is intrinsically related to thermodynamics. On the one hand, it's related to energy, because the Hamiltonian is also the generator of time translation. And it's also intrinsically related to entropy, because of the second law imposes some arrow of time. And interesting approach in order to look at these features of time is to actually analyze specific models of clocks, machines that measure time. And of course, there exist many different models of clocks, for ancient solar clocks to current very high precision session atomic clocks, passing through mechanical clocks, and among many others. And I would like also to mention this review by Gerard, in which he discusses several examples of clocks, of dissipative clocks, with a great detail. There are also models of quantum clocks. For example, some of them coming from the fundamental view are based on energy ladders, and they in coherent states. But these kind of models are perhaps rather stopwatch models rather than actual clocks, in the sense that you need to prepare some initial state. And then when evolution goes on, there is a degradation of the properties of the clock, so that at some point you need to reset the clock. So this is like quitting the watch when this gets off. So for this talk, it will be I will focus more on another type of quantum clock models, meaning continuous quantum clock models, as the one introduced in this reference by Erker and collaborators. Here you have a pointer or a clockwork, which is a quantum system that continuously produces ticks and transfers this information to a register where it is stored. And in order to do that, it uses some resource, like for example, heat coming from a hot reservoir, and it has also some waste, like heat coming out to dump into the cold reservoir. So in these models, you have a continuous time reference, you have explicit information readout, and you account explicitly for the resources. Another important property is autonomy in this type of models, in order to not have another hidden clock, so no external extra sources of control or timing that requires already another clock. So related experiments to these models of continuous clocks have been developed in the group of Natalia. She already this morning mentioned two works, one with nanomechanical resonations and another, the more recent one, with the double quantum dot. And in this context, what I am more interested in is in how the properties of the clock can be enhanced by increasing the complexity of the clockwork mechanism. As discussed, for example, in this reference by Swarthans and collaborators, as long as you so essentially the role of the clockwork is to transform an irregular set of or signal or events coming from a noisy source into a more continuous source And in order to do that, you may consider increasing the complexity of the clockwork, which in this reference is understood and as increasing the size of the clock. So the main motivation for our work is essentially to ask whether one can use a time crystal as a clockwork for one of these types of quantum clocks. And in that case, how the time crystalline properties can enhance the quality of the clocks and how much it does cost in terms of dissipation. So quantum time crystals are considered a new phase of matter where the time translation invariance spontaneously breaks, forming some periodic structure in time. They were first introduced by Wilczek in 2012, but after that there was a no-go theorem by Watanabe and Oshikawa that wrote it out in either equilibrium or ground states. So that shifted the focus to either strongly periodically driven many-body systems that leads to so-called Floquet or discrete time crystals, or to open driven dissipative systems like the boundary time crystal introduced in this reference on the right, which will be, we will focus on this kind of time crystals. So this type of time crystalline phase has been indeed observed in the laboratory in different platforms. Here I just put two examples, one using atom cavity systems and another one using a solid state platform with exciton polaritron condensates. So let me now just introduce a bit what is the model of time crystal we use in our paper. So we consider ensemble of spin 1/2 particles to have n spins that will interact with a non-equilibrium environment. And the non-equilibrium environment is essentially composed by two parts. One is a bosonic bath, so thermal equilibrium, and the other is an environmental mode which is prepared in a coherent state, alpha. So the spins and the bath interacts with the Davis-Cumming model for this collective oscillation, so collective, excitations. And the coherent mode does not interact directly with the system. It just interacts with some of the environmental modes and drive the modes of the bath temporarily out of equilibrium before interaction with the system. So using a collisional-like derivation, we can obtain the evolution of this system through a master equation in lambda form, in which we have like emission and absorption of collective excitations that are given by these coherent jumps. So these jumps are essentially proportional to the collective operators of the spins, but they have some extra displacement that comes essentially from the amplitude of so it's proportional to the amplitude of the coherent mode. So even in this case, we have a local detail balance relation between emission and absorption events at the temperature of the bath. And this displacement parameter is essentially what will control the phase transition in the system. So this is essentially a variant of the time crystal model, boundary time crystal model introduced in that previous reference. Here we have a finite temperature. And closely related implementation has been done in this paper by Ferioli and collaborators. So indeed, in the macroscopic limit, when the number of spins goes to infinity, we recover the same time crystal phase transition, in which so if this parameter lambda is less than 1, we get some stable fixed point for the magnetization. But if lambda is greater than 1, we see like persistent oscillations of the magnetization, as you can see in the picture in the top right, at a frequency that essentially depends on this parameter and gamma 0, which will be just the spontaneous emission rate in the model. So that happens in the macroscopic limit, but if you go to finite side systems, you don't get these oscillations. What you get is a relaxation to a steady state in which there is no apparent time crystal behavior. So essentially you get a non-equilibrium steady state, and any initially present oscillations dump out as time goes on. So in this, you can see an animation of the total magnetization falling down to the non-equilibrium steady state. So the last ingredient of our clock model is to introduce monitoring of the environment. And we do that by measuring the energy change in the bosonic modes of the bath. So, or more precisely, in the interface of the bath with the system. So we perform a microscopic derivation of an stochastic Schrodinger equation, which has this form, which, as usual, you have some smooth non-unitary evolution, and then you have jumps which are proportional to these coherent jumps that I show you in the master equation. So this describes the conditional evolution of our system given a particular measurement record that essentially contains the number of the different jumps that occur during the evolution. So an important point is that by measuring, by monitoring the environment, we can see actually a reminiscence of the time crystal phase even at finite size, and this manifests best in the collective behavior of these coherent jump operators. So you see like bursts of excitations going on time, while if you perform a different unraveling or a different measurement in which you just look at the like the simpler jumps as on the collective spin operators, you still can see some features, but they are pretty washed out. So in the animation, you see essentially a trajectory of the total magnetization over time when you are monitoring the system, so condition on the measurement outcomes. So you can indeed appreciate this reminiscence of the time crystal phase at finite n when you look at the number of counts, the number of jumps that you see over time. So for example, the blue line is, so you can see this specific step-like behavior, which is not present in the fixed point phase. It only appears in the time crystal phase, and indeed the number of jumps is really higher than in this phase than in the other one. So you can see in the axis. So this is in particular for emissions, only emissions, and if you compute the Fourier transfer of that signal, you really appreciate peaks not present in the fixed point phase that are roughly given at the frequency or multiples of the time crystal frequency in the thermodynamic limit. So we want to use this collective behavior in order to define or to define the ticks of our clock. And what we do essentially is that we count a specific number of jumps. So when this number of jumps reaches some threshold m, we count a tick. So these ticks are first passed times, pi, and we will be especially interested in waiting times, meaning the time between these two of these stochastic ticks of the clock. So for the counting of jumps, we can choose, we can make different choices. So we could, for example, take only emissions, or we can count all the jumps, emission and absorptions, or you can also focus on things like the net current, so like the jumps out minus jumps in, which will be proportional to the heat. So in order to quantify the quality of the clock, we have these measures that are based on the waiting time distribution, the waiting times. So we focus on resolution, which is 1 over the average waiting time between ticks, meaning how fast your clock can produce ticks. The accuracy, which is like the inverse relative error in the waiting times, which tells you how similar are the ticks of your clock. And then also the Fano factor, which is essentially noise to signal ratio, and it's a compromise between resolution and accuracy. So it's 1 over resolution times accuracy. So when looking at these quantities, we can observe this accuracy resolution trade-off. This is so a good clock, of course. For a good clock, you will want to have as much resolution as possible and as much as accuracy as possible. But it turns out that these quantities generally verify a trade-off. So essentially, in the case of Poissonian random events, this trade-off goes like essentially 1 over, the accuracy is 1 over R. So the more accuracy you want, the less resolution you have. And indeed, this is the similar behavior we see in the case of the fixed point phase in our system. However, when we go to lambda greater than 1, so in the time crystal phase, what we see is that this trade-off gets some interesting structure with these peaks that points to, let's say, optimal choices for the thresholds. Because so we can move on these curves by changing the number of thresholds, so changing the thresholds of the number of jumps we use to define a tick. So in particular, we will focus on this point here, which will be the optimal one, because it also minimizes the Fano factor with respect to the other, let's say, peaks in that plot. So doing that, we can appreciate enhancements in the clock properties. So if we look, for example, to the accuracy, you see the accuracy, this red line is for 50 spins, the blue line is for 100 spins. So when you cross the critical point lambda equal to 1, this quantity starts to grow. For large lambda, they scale as proportional to lambda. And if you look at the resolution, well, there is some like spatial behavior close to the critical point, but after passing the critical point, you get a scaling that goes like that, which is essentially another time the frequency, it's roughly the frequency of the time crystal in the macroscopic limit. So what you can also appreciate is that you have better quality when increasing the number of spins. So, and this goes with the square root of S, the total spin, while the resolution remains almost constant when you increase the number of spins. If you look at the waiting time distribution, you can also see that this shrinks when increasing the number of spins, but this happens only on the time crystal in phase. And moreover, it displaces to the left and reduces the variance as you enter more deep in the time crystal phase, so increasing lambda. Okay, so we are also interested in the thermodynamic cost of this system. And in order to do that, we have to compute entropy production, meaning the dissipation in the system, for waiting times. And this is not completely easy. And we need some suitable definition of entropy production per tick, which is something which will be stochastic. So we will involve the stochastic times. But using some previous result in this paper, we get some expression for that, in which you have some entropy change in the system defined with these Schumacher fidelities of the conditional dynamics of the system over the non-equilibrium steady state, and then the stochastic heat, which will be just counting the emissions and absorption during that period of time. So with this definition, we can prove a fluctuation theorem for this entropy production, and we can recover a second law for these ticking times of the clock, which is very non-trivial. Here you can just see some of the checks we did for the fluctuation theories for different types of counting of the emission, absorption, etc. So if we evaluate this thermodynamic cost, what we see is so we compare the entropy production and the dynamical activity in the system with the accuracy, and look at the bounds like the thermodynamic uncertainty relation, which imposes a bound on the accuracy of the current. But of course, this only happens. So here, the different lines are different choices for the counting events. So the orange one is a current, while the red and the blue are just taking emissions or all the emission and absorption. So as you can see, only the one that is a current is bounded by the QR, while the other ones can go over the QR and are only bounded by the kinetic uncertainty relation. So this suggests that it may be more intelligent to use observables that are symmetric under time reversal and not currents in order to measure time, because currents will be much more bounded. So for large lambda, we indeed recover a linear behavior for the accuracy and the entropy production per tick and the dynamical activity per tick, while the scaling of with the number of spin is proportional to S, so that the scaling of the entropy production per tick is greater than the one of the accuracy, so one goes with the square root of the other, meaning that there is no freelance. So this is a dissipative clock, that in order to increase the accuracy and the quality of the clock, you need to dissipate more, of course. So let me just finish with some take-home messages. So I presented a quantum time crystal clock model, which is based on a non-equilibrium environment. Here we have coherent jumps that exhibit some non-trivial time correlations, and this means that optimal thresholds exist in order to define ticks. The accuracy is enhanced in the deep time crystal phase, and the number with both going deep into the time crystal phase and increasing the number of spins. But of course, this comes to a price, which is increasing dissipation, with a manifestation of the second law, in which we formulate these ticking times. So finally, the violation of the QR and saturation of the QR suggests that superiority of time-symmetric observables versus currents, at least in this system. So as an outlook, we may pursue some more precise experimental implementation of this kind of models, comparison with other time crystal models. And another interesting point that also Natalia mentioned this morning is the cost of the signal amplification, because there are probably models of a smaller system that performs better than this one. But of course, this has the advantage that the signal that produced is already really macroscopic, because it's really burst of emissions. So what I would expect is that you will not have so much cost on the signal amplification, because the clock itself is really giving a greater signal because of the collective effect. So with that, I would like to finish, and thank you for your attention.
Let's thank the speaker. We went a little bit over time, so there won't be any question. Just going to ask him questions after the next speaker, who's going to come up now.